Good morning. My name is Konnie. I'm a PhD student from the Department of Computer Science at Hanyang University. Today, I will introduce my research on zero-shot recognition. This is the content of my presentation. Zero-shot recognition is the cognitive ability of categories that have never seen before. In case of human, even when only high-level description is provided, we can visually create the unknown category by combining visual characteristics of what we already knew. The purpose of the zero-shot recognition study is to model a machine with this capability so that the model can visually classify categories with no training sample. Previous works on zero-shot recognition have proposed diverse methods of learning a direct mapping function from low-level visual feature space to various kinds of semantic embeddings containing both seen and unseen categories. The semantic embedding space can be divided into two types, explicit and implicit type. Explicit type is a type of semantic embeddings where relationships between seen and unseen classes are explicitly described, such as human annotated attributes. This type has the advantage of knowing the meaning of each element of the embedding vector, but the disadvantage is that it has to be predefined by an expert that makes it costly and not extensible. Implicit type is a type of semantic embeddings that are learned from large text corpora in an unsupervised manner. Word embeddings belong to this type. The relationship between seen and unseen class can be measured by Euclidean distance or cosine similarity. Word embeddings are constructed using machine learning technique, so they have an excellent extensibility and widely applied to zero-shot recognition models. However, we wondered if conventional word embeddings would be the best choice for zero-shot recognition. Since the corpus used for learning word embeddings is a source that contains only text domain information, it may be inherently biased toward text domain data, and as a result, the word embeddings may have different semantics from the real world. This bias makes two heterogeneous domains more independent from each other, resulting in the mapping function being more likely to be poorly trained. If not only text domain sources, but also visual domain sources can be used for learning semantic embeddings, the independence between the two heterogeneous domains would be relaxed, so the zero-shot recognition model will train the mapping function more properly. In our work, we propose a novel learning strategy for semantic embeddings with both informations from text domain and visual domain to overcome the shortcoming of the two types of semantic embeddings. Our contributions are to learn visual context embeddings that contain visual domain information that can be applied directly to various zero-shot recognition models, and to define the visual domain corpus for VCE learning and propose the contextual distance required to construct the visual domain corpus precisely, and also to quantitatively verify the improvement of applying VCE on two data sets compared to when apply existing word embeddings. Words that frequently appear close to each other within a document will have a high degree of similarity to each other in word embeddings. Likewise, objects that frequently appear simultaneously in an image have a high probability of being related to each other. Therefore, a large data set in which several objects appear simultaneously in one image can be regarded as a visual domain corpus and can be used to learn the embedding of each object labeled with no bias toward text. Figure 1 indicates the process of building the visual domain corpus for learning visual context embeddings. To build the visual domain corpus, we first collected all annotations including object labels, bounding box information from an image dataset as shown in Figure 1. The gray rectangles in Figure 1a is the bounding boxes of objects appearing in an image. Figure 1b shows the annotations per an image. In order not to violate the zero-shot condition, low-level visual data is not included in what we collected, but only high-level descriptions such as labels of objects and the bounding box information are included. Based on the bounding box information of an image, other objects located close to the target object were defined as the context of the target as shown in Figure 1c. It is intuitively acceptable that various objects included in a single image share common contextual information, and objects appearing around each other in multiple images are highly likely to be related to each other. This is very similar to the relationship between words in the text corpus. From this intuition, we decided to learn new word embeddings from the visual domain corpus consisting only of annotations on image datasets. We named these new word embeddings visual context embeddings because it has learned the visual context from the visual domain corpus. The embedding model of visual context embeddings is the same as the embedding model of globe. In the same way as using the global co-occurrence matrix of words in globe model, VCE model learns embeddings using the global co-occurrence matrix of objects in the image dataset. We learned VCE using the same cost function as globe. To apply globe's decreasing weighting functions to VCE, we calculate the distance between the central objects and the surrounding objects from the bounding box information. When calculating the distance between two bounding boxes, using the Euclidean distance between the center points of each bounding box is the simplest idea. However, Euclidean distance is not suitable for measuring the contextual influence between two objects. For example, as shown in Figure 2, even when the Euclidean distance is the same, the correlation between the two objects may vary depending on the size of the bounding box. We propose a contextual distance which should obey the following properties. 1. As the Euclidean distance between the center points of the two bounding boxes increases, the contextual distance should also increase. When the Euclidean distance is 0, the contextual distance should be determined by the width and the height of the bounding boxes. 3. The contextual distance of the bounding boxes with the same center points and with the same size should be 0. 4. The difference between x and the difference between y of the two bounding boxes should be normalized by width and height respectively. Property 1 can be accepted intuitively. Property 2 is necessary to consider the case shown in figure 3b. Property 3 refers to the case where the two bounding boxes are exactly the same. In order to generalize the case shown in figure 3c, we need property 4. The contextual distance, taking into account all the above properties, is defined as below. In the next section, we will introduce the details of the experiment to show the effectiveness of BCE. First, we will briefly mention the experimental details for the learning visual context embeddings. We used the visual genome dataset and the Microsoft COCO dataset. For the zero-shot recognition setting, we need to split the seen and the unseen classes. In case of the BG dataset, there was a study using the BG dataset among the existing zero-shot recognition studies, so we decided to use the same class split setting used there as well. On the other hand, in case of the COCO dataset, we could not find any class split that we could refer to. So we randomly selected 20 classes out of 80 classes and set them as unseen classes, and the remaining 60 classes were set as seen classes. For training BCE, only the annotations of BG datasets are used. These labels were mapped to the WordNet synsets. We scanned all annotations in the BG dataset and included only about 3,000 labels in our vocabulary. We followed the learning process of GLOBE to learn the visual context embeddings. After learning visual context embeddings, we apply them to the zero-shot recognition model for quantitative evaluation. For the generalized comparison, we trained 4 different zero-shot recognition models with existing word embeddings like skipgram, globe, and visual context embeddings respectively. To reduce errors due to the degree of model parameter tuning, we trained and tested all models 7 times. The tables in this page show the 4 zero-shot metric scores of our experiments on various zero-shot recognition models. The values in the table show the mean and the standard deviation of the results of 7 tests. The values indicated in bold means the best performance for each metric. The experimental results show that BCE obtained high scores in classic zero-shot metric and the generalized zero-shot metric for the unseen classes in both the MS COCO dataset and the BG dataset for all zero-shot recognition models. Therefore, we can conclude that BCE has a significant effect on improving the performance of the zero-shot recognition model in general. These are our qualitative results. The figure 4 is a visualization of the 32-dimensional BCE using TSNE. It can be seen that the embedding vectors are not evenly distributed, but are clustered among those with high semantic similarity to each other. Table 5 shows which labor embedding vector has the highest cosine similarity to the target labor embedding vector. According to this table, the overall embedding was performed well. Additionally, the embeddings appear semantically acceptable when the number of occurrences in the dataset is 200 or more. In this paper, we introduced a new approach of semantic embeddings which we named visual context embeddings by learning the visual context of words appearing in image datasets by using the annotations of the image dataset. For embedding visual context, we defined a new formula for calculating the contextual distance between objects in an image and experimentally proved that this formula is suitable for estimating the contextual distance between objects. However, there are clear limitations to this proposed work. For example, since a part of VG dataset was used for the VC learning, the embedding classes had to be limited to the classes existing in VG dataset. Therefore, as our future work, we are considering experiments in large-scale datasets such as ImageNet to prove the generality of VCE. Thank you for listening.